and welcome again to an applied math lecture. Okay, so we'll start today with some definitions. So here is lecture 8. Okay, so before anything, let's do some definitions and clarifications. Okay, so there you go. Now, ODEs, ordinary differential equations, right? There, we can classify them into two categories as they depend on time explicitly or not. So we would have autonomous ODEs. Okay, so these are, for example, so it's something that looks like this, where X, let's say, is in a domain in Rn. Okay. And non-autonomous, okay, so these are the ones where the right-hand side depends explicitly on time. Okay, so let's say X is in D, and then T is given in some interval in R. Okay, I'm not getting into the theory of ODEs, right? So if you want an example, right? So for instance, an example here would be, let's say, X dot equals X squared plus T, whereas here as an example, X dot equals X squared plus 3X. Okay, okay. So that's the main difference, you know, so you have in the right-hand side T explicitly or not. Okay, and yes, Varahi, you put the assignment in the Dropbox in my learning space. I'm going to take this chunk out from the video, but yes, we put the assignments in the Dropbox. Where else? Yeah. Okay. I think I put there, made a folder, no? Assignment 1, did I?
I just checked now, so I didn't see it. So
okay, so if I didn't do it, I'll do it for sure. Okay, good. Thank you for reminding me if I didn't do it. I thought I didn't, but anyhow, it's possible. Okay, so now
Professor?
yes.
Sorry. Were you done? Whoever was speaking? Okay. I just want to ask, when you're writing x equals fx, I see a little dot. I don't know if it's just my screen, but is that supposed to be there? Is that supposed to be like a, is it like a dot or is it a hat over the x?
So what is the dot meaning? It's a good question, actually. What is the meaning of the dot in all our stories here?
derivative.
Okay, so we're talking about ODEs, right? So the dot, it's a shorthand for dx dt.
Okay.
Yeah?
Okay.
Okay, all right, good. Yeah, it's a generally derivative, yes. So that's the meaning of the dot. Anyhow, so good to ask, because if you don't ask, you don't know, you know? Okay, so yes, it's a dot. It's just to not write dx dt, yeah? Okay. Okay, so everybody knows this. So I'll take this away anyhow. So now you know this. Okay, so I'll take the break to do the cut in the video. I'm getting an expert to be at editing. So okay. Okay. So autonomous and non-autonomous. Fine. All right. So then let's say we have okay, something like we have an ODE in Rn. So X, right, would be something that has n entries, okay? And then we have an ODE that looks like dx here. I'm going to use the dx dt, okay? Equals f of x1, x2, xn, right? But this is a vector too. So this f is defined on the domain in Rn if you want, and takes values in Rn, right? So we have this given ODE. Now, we have to define the phase space, okay? The domain, okay, the region, let's say, in the region D, okay, the region D in Rn, where x belongs to, or to which x belongs to, I don't know where x, let's say, belongs, okay, is called the phase space. And I'll have an example for you. And then the set of solutions of, let's say, equation star, let's call it star. Okay. So the solutions will look like some x1 of t, x2 of t, right? Xn of t. So the set of all these solutions as traced in D form what we call the phase portrait. Okay, so that's another one. The trace, if you want, or the graph of one solution is called an orbit. Okay, so if you want, the phase portrait is formed by orbits. Okay, so we have to have a denomination for this, and I'll have an example for you right now. Okay, all right, so let's see it on an example. Right, so here, let's say we're looking at the system in 2D. Okay, so in R2, so we have x dot is v, and v dot is minus 16x. Okay, so it's really like the oscillator with what we did last time. So, so this is equivalent to x2 dots plus 16x equals 0. So it would be like the oscillator with mass equals 1, or, with the omega squared is 60. Right? So I'm just picking something easy, right? So x1, x2, it's xv, yeah? Right, so I'm in 2D, all right? In this case, D is the entire plane, yeah? So the domain, the phase plane, it's really a phase plane in this case. So the phase space is a phase plane because it's in R2, right? So you would have a phase line if it's in R1, phase plane, and then starting with R3 is phase space. All right. And now we want to see if we can draw the orbits. We talked last time about the energy, so we know, right, that the energy is 1 over 2v squared plus 1 over 2 times 4 squared. It was like last time, right? So it's basically yeah, 4x squared, right? So the energy is here 1 over 2v squared plus 2x squared equals constant, okay? So we did this last time, so more or less they would look like this, right? So if we're drawing the phase curves, So we do this, and then these are ellipses, right? So if you want, we can write them as v squared plus 4x squared equals constant, right? So we will have a variety of curves that, okay, let's pick a color. So let's say v squared plus 4x squared equals 4, okay? So this is an ellipse that would have v when x is 0 is as plus minus 2, and then when v is 0 plus minus 1. So I'm going to do it with green. There you go. There's the orbit for v squared plus 4x squared equals 4. Okay, that's an orbit. And then we can do one with v squared plus 4x squared equals 60. I'm picking on purpose nicer numbers. Okay, so v would be plus minus 4. And x plus minus 2 somewhere here. Okay. Or let's say this one we draw it with a light blue. Okay, so this would be here. No, let's try again. I'll try a third time and that's it. You get the idea. Okay. Okay, so this is v squared plus 4x squared equals 60. Okay, so these are orbits, right? These are orbits in the phase plane. So in this case, xv, right, belongs to R2. This is the phase plane as I wrote it up there, right? And these are, you know, various orbits, right? And the first one corresponds to the level of the constant b, 4 being 4, and the, you know, the other one for 16, and so forth. And we have a special, very special orbit, which is this point, right? So this point corresponds to v squared plus 4x squared equals 0. So that's the equilibrium actually. Okay, so there you go. That's your example. All right, so this being said, so now at least, you know, we can talk about the phase space and the orbits and maybe a phase portrait, right? So the set of all ellipses, if they will fill in this plane, would form the phase portrait. Okay, so there you go. So let's move on and start actually what we have to discuss about today. So the first item, so we'll have 2 items to cover. I don't know if today and next time. So the first one, I called it 1D second order conservative ODEs. Okay, and the other one is 1D second order. I'm going to put in between quotes here, damped ODEs. Okay, so damped because they're mainly modeling systems in which we have a damping, you know, some friction going on. So that's the template there. Okay, excuse me a second. Someone at the door. Okay, good. All right, so we'll start with the first item, 1, right? So the template is something that looks like this: x2 dots plus f of x equals 0. So it's a second order equation, right? Which of course we can write it as a first order system: x dot equals v, v dot equals minus f of x. Okay. And I will explain where the word conservative comes from. Well, it's a conservation of energy, but again, you don't really know what the energy is, so we will just deduce it. Okay. So now, if we write the system in this way, so in other words, we can write it as dx dt, like specify was the dot, dv dt equals minus f of x. And here we're going to do the following. So we assume that x, is in a domain where everything is nice and well defined, okay? So if f has some issues like a denominator or something, we're going to take it out of the domain, so we'll just say, okay, x is in an appropriate domain. And f of x is a function that is nice enough that we can work with it, right? So maybe it's continuous, maybe it's discontinuous, but it's specified, okay? Someone gives it to us, all right? So what we're gonna do now, I'm gonna say, look, what about if we divide these equations one to another, okay? So basically, we'll have something like dx dt over dv dt will become minus v over f of x. Okay. And now I'm going to do algebra with functions. It's actually doing the chain rule, but okay. So this implies, if you want, that dx dt times dt dv equals minus v over f of x. And now you can either think that this is a chain, this is the chain rule actually. So we're gonna jump directly to say, well, this is actually dx dv, okay? Or, if you think like a physicist, just do algebra and say, oh, dt with dt is like algebra, they just disappear, we just cut them, okay? But it's in fact is the chain rule there. So this is minus v over f of x. And now, okay, from here, I can actually isolate on one side to have f of x dx, and on the other side, minus v dv. Okay, and now I will integrate each side. So I'm gonna flip the page. I'm gonna write this again so you see it. Okay, so I'm gonna apply the integral sign both sides. So we have integral f of x dx is minus integral v dv, but then I'm going to put some endpoints, right? So let's say we're going to put here from an x naught to some x, okay? But then if I put x up, then I better write inside the integral not x, but another letter, like we can make it sigma or something, right? Because it disappears in integration. And then here, so from some v naught, some initial velocity, let's say, to some current v, but then again, I have to change the name inside the integral because I cannot have v inside and v as an endpoint, right? So instead of v, let's say, I don't know, s, okay? But what I did, I'm just integrating. So what we're gonna end up with, the left-hand side, I don't know what it is, but it will just stay like this: integral from x naught to x of f of some sigma. The sigma equals minus s squared over 2 taken in between v0 and v. Okay, so there you go. From here, we deduce then that, right, so I'm writing it, is minus v squared over 2 plus v naught squared over 2, right? Or we can write it like this. Okay. That's one way to write it. Sorry. So here is a f of sigma, right? Sigma equals v squared over 2. Okay, so now we can say, we can take, say, v of 0 to v 0. And then we can take x of 0 to be x 0. Okay. And we could write this also. So if x in 0 is okay. If there is a value, no, it's okay. Just leave it like this. Okay. So wait, I'm not going into anything anymore. So the point is that we can we end up with something that looks like this. Okay, and that constant can be taken as the value of 0 at the velocity at value 0, right? Is that constant? And this is nothing else in truth but the energy conservation that last time we discussed, like I came with it from my pocket, right? So in this case, we kind of deduce it, right? So this is an integral of motion, as we called it last time, okay? And in fact, is the conservation of energy, okay? Where we have T to be the kinetic energy, okay? Define it as 1 over 2v squared. And V, let's say, so this here, V is the potential energy. Okay, so it's actually a V of x, and is integral x naught to x of f of sigma d sigma. I'll do some examples. Okay. Okay. All right. And so I'm going to flip the page. Right? So for this system, so for x dot plus f of x equals 0, we always have the energy integral of motion given by 1 over 2v squared plus integral from x naught to x of f of sigma d sigma equals constant, okay? And this constant is these guys at time 0 if you want. So it's 1 over 2v in 0 squared plus integral from x naught to x in 0 if you want, okay, of f of sigma d sigma. So this kind of stuff shouldn't scare you. It's just what is the value of the left-hand side at time 0, okay? So let's do an example. I'm going back to so let's say we take x2 dots okay, minus 1 over x equals 0. That's an f of x, yeah. So what would be the integral of energy? Would be 1 over 2 v. So if you want, this is equivalent to x dot equals v, v dot equals, let's put a plus, minus 1 over x, okay? So the integral of energy will look something like this, of minus 1 over sigma d sigma equals constant. Okay? So that's f of x is this guy. Okay? So now if I'm doing the integral, so it's 1 over 2v squared plus 1 over sigma squared, taken in between sigma is x naught, or x in 0 if you want. We can put here an x in 0 actually, so it's just some value that is fixed. Let's put it x in 0 because it's easier, right? So maybe x naught, because then you'll be confused. So x naught, and then sigma is x equals constant. So 1 over 2v squared plus 1 over x squared minus 1 over x naught squared equals constant. Okay, and this will be the value that we have at time 0. So here, I'm going to write this one now. So what is behind this? Okay, what this hides? This x of t, right? So this x and v are function in time. They represent the position in time and the velocity in time, right? So this is saying that at any time we have this relation going on, right? Equals 1 over x naught squared plus constant. So this plus constant here, this is another constant, right? And what would be this constant? Okay. Oh, it will be whatever is value at times 0 squared. Okay, so let's write it again. So 1 over 2 v squared of t plus 1 over x squared of t will be, is constant in time. And what will be that constant is what these functions have as value at time 0. Okay, so there you go. So if you want, we can write it like 1 over 2v naught squared plus 1 over x naught squared. Okay, point is that is whatever. So for every initial condition, we'll have a different constant, right? So every set of initial conditions, every position and velocity will give you a different constant, which will define another curve in the phase plane. Okay. So now we can say, okay, so the phase plane okay, OXV, because that's the plane, for x2 dots minus 1 over x equals 0, is filled by the phase curves or orbits, right? These are the orbits, okay, given by 1 over 2v squared plus 1 over x squared equals constant. Okay, and then here is, I'll let you do this. So you can take a plane and see how these guys are looking, x and v. And obviously x cannot be 0. So this line is not in the domain, right? By the way. So in this case, x belongs to r less 0. So you can do drawings. So here, homework, little homework, okay? Draw some orbits, okay? So in other words, take some constants and do the profiles, okay? Okay, So that's one item we have to discuss today. So the next one is I'm coming back to this thing of the conservation of energy. So, okay. Going back to 1/2 b squared plus integral x naught to x of f of, I'll put an s. Okay, equals, okay, so it says 1/2 b naught squared. Okay, all right. So that's the energy conservation. We want to respond to look at a different problem. Okay, so okay, this kind of relation is also very important for calculating the time of travel. So I'm going to write here, calculating the travel time between two given points. Okay, so what I have in mind is the following. Let's say we have here in the phase plane 2 points. So let's say A and B, okay, that are on a orbit. So these points are on, they're both on the same orbit, because otherwise we cannot calculate anything. Okay. So here somehow I have an orbit in this plane. So here maybe I'll take, you know, like one of those ellipses that we did earlier. Okay. So let's say I'm taking here, you know, a point on this ellipse here, and I want to compute the point here. So this is A and this is B, right? But, you know, the problem can be put in general, right? So if I have, you know, if we take 2 points on an orbit, so let's say we have an orbit that maybe looks something more interesting, okay? So something that is like this, okay? So I made it this way, okay? I didn't mean to. Okay, and I have a point A here and the point B here. What is the time to get from A to B? If we know that this is, so this is a phase curve or an orbit, this is an orbit of x2 dots. Okay, so let's write it first orbit. Okay, so I'm taking an orbit of our system and 2 points on the orbit, and I want to compute the time to get from A to B. Okay, that's the question we want to answer. So this is basically, here I'm gonna change the, so this is, okay, so it's something that goes from, if I'm starting on the orbit somewhere, so let's say this is my x naught, b naught, right? And I'm starting and I'm going that way, right? So it'd be the time that I'm at A, you know, or the time that I'm at B minus the time that I'm at A, fine, okay, of dt. Okay, and now comes, you know, the cheeky stuff. Right? So I'm going to do the following. I'm going to write this, okay, as dx dt times dt dx. You're going to say, what are you doing there? It's like I'm multiplying by 1, okay? But I'm writing that 1 is like the inverse function theorem. That's what it is, actually, right? As dx dt, and then I'm dt dx. So if you want to think like the physicist, algebra it is, okay? I don't mind. So there you go. TAB will be TA to TB, and you'll see why we're doing this. So we don't want to pass from this dt to something that we know, okay, to calculate, and we'll know it from this one. Yeah. So this is dx dt, right? Times, actually, I should write it the other way around. So it will be 1 over dx dt times dx dt. Okay, so I'm doing some mumbo jumbo. Okay, I recognize that. But this is just because, you know, here, these two guys, they will combine into the dx. And this fellow is nothing else but the v. So actually, and I'm doing a change of variables, to be honest, right? That's exactly what I'm doing. So I'm going from t to x of t. So here I can write, okay, so this will become, okay, integral. So I'm going from t to x of t. It's a change of variables, okay? So it will become from xa to xb of dx over v. I'm going to say, so what did you do with that? Well, that's where this one comes into play. Okay. So let's call this E from the energy relation, right? So E, I'm going to write it as 1 over 2 v squared plus integral of, okay, let's call that one v of x, because that's what it is the potential, okay? Equals constant, and let's call that constant h, okay? H from energy, it is something that people use all the time, okay? So it's constant, okay? So for various h's, various levels of energy, right? But this is, you know, if I go one step further, this is equivalent to v being plus minus root of 2h minus v of x. And I repeat, v of x is nothing else but this guy. It's a notation. It's the potential. Okay. So it's no. Okay, so I'm going to go now with this fellow. And I'm going to substitute it into this. And here is what we're going to end up with. TAB equals integral from XA to XB of dx over, well, I'm going to put plus minus here because we don't know which one it is, but that's minus capital V of x, yes? So don't confund it with little v, so maybe I should do little v. Okay, so let me write it nicely for you. Okay, so I'll do it. I'm not doing anything but writing it nicely. So TAB will be integral from XA to XB of dx over, okay, there we go, something like that, right? And here, I'm not sure what sign to put. So it depends on the problem, right? So if you go backwards in time or forwards in time. So I'm gonna just leave it like this. There's the formula. And now let's do an example to see exactly how this is working, okay? So it might look like a mumbo jumbo. The point is that for this kind of system, but only for this kind is happening, okay? Because of the energy conservation, because of this integral of motion, we actually have a hands-on way to compute the travel time in between 2 points. This is the philosophy. So once again, you know, for systems of this form, but only for these guys, the travel time in between 2 points on the same orbit can be computed. And then can be computed essentially because we can use the energy integral to substitute the velocity with something as a function of position. And this is this relation here. Okay, so let's do an example. Okay, yeah, I have it here. Okay, so for example, okay, let's say we have 1 over 2 v squared plus 8x squared equals h. Okay, So V in this case is 2H minus, okay, sorry, here it's a bracket that is missing, right? Put the bracket in, put the bracket in, yeah? So I'm bringing to the same denominator, 2H minus 2B. Bracket, bracket. And this is little b. Okay. So 2H minus big B of X. So what is, okay, so where is this one coming from? Is X dot equals V. V dot is, so this is 1 over 2 omega squared, right? So it's omega 4x. Okay, so that's the original system. And this is the associated integral of energy. Okay. No. Let's get confused about this. There we go. That's omega squared, right? Yeah. All right, so in this case, we have V plus minus root of 2H, so H is a constant, yeah. Minus, so this is the V of X, right? This guy here, 8X squared. Yeah, that's the energy conservation. All right, so now let's say we take here the orbit corresponding to this being some value, I don't know, give me a number, 20? Okay, I won't compute it anyhow, but I'm just saying, okay, so here is this orbit corresponding to this value here. I'm going to make it. Okay, so this is 1 over 2V squared plus 8X squared equals 20. Okay, all right. And now let's say we take the point A here and the point B here, and we know it's going down that way because we talked about that last time. And we want to know what is the time that takes from A to B. Okay. And as we compute it on the other page, this would be something like this. Okay. For now, right? The issue we have is this guy. Which one do we take and how do we take it? And that's when we start, we have to look actually at the picture, right? Okay, so that's of course an XA, yeah, okay, yeah, okay, good. Yeah, I just made it XA, yeah. Here was an XB by mistake, but this XA, of course, it is. Okay, good. So I'm coming back to the problem. What do we do is a plus or minus, right? But remember this guy here. So what is this? This is, we shouldn't forget that the formula actually is XA to XB dx over V. That's where it's coming. V being the velocity, being the V in the picture. So this is the x-axis and this is the v-axis. And now I'm going to look where V is positive and where V is negative to know what sign I'm going to put in there. Right? So V is positive here and V is negative here. And here I have a break, right? Where V is 0, there is a break. So I'm going to split this integral into 2. Right? So in this problem, TAB will be integral from x in A. So this A has x0 And V, I don't know, some height. Actually, we can calculate what is the height here, right? So from this one, if X is 0, then V will be plus minus 40, plus minus root of 40, right? So we actually know those values. So here would be a root of 40 up, and this one would be 0 and the minus root of 40, if I am to compute them. But I need just the XA, right? So XA is 0, so I'm going to put a 0, and then here is where is breaking, and whatever I'm going to put here is with plus. So this will be the bunch with plus. So I picked H to be 20, so this is the H, minus 8x squared, plus, and I'll have the other one that will go to 0. Okay, so I have to put here what is this X cut, if you want, or okay, let's call it point C, okay? So the XC, what is XC? What is XC? Okay, well, XC is that for V equals 0, right? So we'll have 1 over 2 times 0 squared plus 8xc squared is 20. Right? So there you go. XC is plus minus, but okay, we put the plus one, right? I'm gonna make it again for you guys to see. So this is the domain where D is positive, and this is XC from cut. Okay, so when it's 0, this will be root of 10 over 4. Okay, whatever, yeah. So it's actually root of 5 over 2. There you go. So this guy is root of 5 over 2. Okay, so here, from XA, which is 0, to XC, which is root of 5 over 2, plus the stuff from root of 5 over 2 that goes down to XB, where X is 0 again, dx over minus 220 minus 8x squared. And then we can compute it. And actually we can see, because, you know, by symmetry, this will turn out to be twice the upper part, if you want, right? So there we go. And now how you compute this, now, luckily for you, I'm not asking you to know how to compute these antiderivatives. You know, if you ever get one of these in a test or something, use Maple, use whatever you want, okay, to give me a number. So you get up with a number. If it's not a number, then you're in trouble. Okay, so there you go. Nobody said that mechanics is easy, right? Okay. So you have a little example here. So you have to think about it. What is going on? The philosophy, I repeat, the philosophy is very simple in its, you know, 2 words. For a system of this form, we can compute, and so this form, we can compute the travel time from a point to another on the same orbit using the energy conservation. Well, ta-da, that's it. That's in a nutshell. Okay. There you go. Okay, so this is this is just page 2 from my notes, and I have up to 9, huh? Anyhow, so we'll do one more item today, and then I'll let you go. Okay. All right. So this was the first item. So the second item, again related to this 1D conservative system. So why do I call them 1D conservative systems? Okay, see, conservative. It's because they conserve energy, right? So we get this integral of motion, which is in fact the conservation of energy. Okay. So for the physically relevant systems that are modeled by this type of ODEs, okay, this integral of motion that we get, you know, doing the mumbo jumbo with calculus is in fact the conservation of energy. Okay, that's where it's coming from. And now here I'll show you a different thing that is, ooh, I made the page. Okay, that is absolutely gorgeous and is one of the first things I actually learned as a grad student, right? So it was one of the first things, you know. I mean, it was done as an undergrad, but you know, when I was an undergrad, I wasn't a super diligent student. Let's just put it like this. I had other priorities in life at the time, but then you know, I kind of defined other and so forth. Okay, so there you go, regions of motions. Regions of motion. Yeah, it's just gorgeous. Okay, so I'm going back to our systems, okay? And then we're gonna define the potential energy, right? So we have defined, I predefined it, but let's do it again, okay? The potential energy, okay, is the function v of x, which I'm gonna define to be integral from x naught to x of f of s ds, okay? So where, okay, so x naught can be anything. So could be the initial condition. It doesn't really matter because why am I not worried about this value here? Okay, it's because in effect, you know, what is this system that I'm writing is corresponds to the derivative of the function, and the derivative of the function of v of x of capital V is actually little f of x. It doesn't matter the endpoint on the bottom. It doesn't matter what I write there, okay? And as a matter of fact, there is a clear definition in physics that says very clearly what is the potential of a system. Oh, is a function for which the derivative gives us the vector field on the right-hand side, gives us the f of x. Okay, but I'm not going that path. I'm just saying, look, you know, let's just take it like this. Right, so we take it as a definition, is the potential energy is the integral from some value to x. I'm not putting, I could put here a 0, right? So let's say 0 to f of s ds. But okay, what about if f of s is actually 1 over s? See, like you have a denominator with 0. I cannot put the 0 as the end. Then I have to do indefinite integrals and whatever. So I'm just avoiding that. I'm just saying, look, you know, it's a value there. It's fixed. Could be the value at times 0. If you feel comfortable about that, is the value at times 0. But essentially in the problem, in the ODE, it doesn't really matter what we put in there. Okay? It matters when we do the phase portrait, but that's the phase portrait is made by curves that are level sets of the energy, and the level set is a constant that is given by the values at the initial time, right? The initial values in the problem. So that's where I will know what to write there for x naught will be the value at the initial time of x of t. Voila. Okay. I don't know if I made sense, but anyway. Okay, so okay, I'm coming back to this thing with the regions of motion. So once we have this, okay, so let's call this 1, and then we have attached to it immediately the energy conservation that says that 1 over 2v squared plus this v of x equals constant, okay, and I called it h, right? Where h, we have this convention, represents a constant, and then, okay, so if you want, okay, this h would be the value of these things at time 0. It's the easiest way to kind of, okay, so we can say 1 over 2 v naught squared plus v in x naught, okay? But then if you write v in x naught, okay, take care with that. Anyhow, so it's okay, you can write it like this. The point is that this constant, this h, is decided by the values at time 0. Fine. So here they are. I have the object of interest, and the wonderful conservation of energy. And here is a very basic fact that is used even, you know, by these big professors that are doing all kind of interesting chemical experiments and whatever. Okay, so I'm going to observe the following. 1/2 v squared equals h minus v of x. Yeah, you see what I mean? So from that relation, I get that h minus v of x, well, this better be positive all the time, right? From where we get that v of x has to be less equal than h. Okay? From where we get that actually x belongs to the domain. Okay, so this is in B, R or something. So is those values of x for which v of x, right? So those values of x for which v of x is less equal than a constant. So you're gonna say, okay, well, you know, you just wrote this one in a different way. Yeah, I know that I did. Yeah. Okay. Now, this thing here will define the regions of motion. I'm going to call them like this for x. Okay. So maybe. Okay. So let's see, why am I saying this and what the heck, how am I going to use this? Okay. So let's do it on an example. So let's take back our wonderful x dot is v dot is minus 16x, okay? And then we had the energy for this one, 1/2 v squared plus, right? So this was the little v squared, plus 1/216. So it was an 8x squared, right? Equals h, okay? And then I'm getting that because 1/2 v squared is h minus 8x squared. So I'm redoing the logic of it. Then we end up that 8x squared must be less equal than h, yeah? Where h fixed level of energy. Okay. So let's do a drawing and let's see what the heck is going on. Why I insist that this is such an important thing. Okay, now the truth will be revealed. Okay, all right. So what is this 8x squared? Oh, it's a parabola, right? So this is what I'm drawing here is v of x, right? So this is, if you want, v, sorry, this is not a v there. So y, this is a y. Y equals v of x, right? So in this case, y is 8x squared. And now I'm going to discuss the regions of motion as the energy is a priori fixed, okay? So the energy in the system, okay? So the energy, which we call h, is basically 1/2 v squared plus 8x naught squared. So it's where the velocity was initially, okay? So it's the same thing, that's x naught is, okay? So that's the energy. And now I'm starting. If the energy is negative, and I'm going to do a level of it here, okay? There is no motion. The motion is impossible, okay? Okay. And you're going to say, what do you mean? Well, okay, so this is because we cannot have, there is no way we're going to have 8x squared less equal than some h that is negative. Okay, so this is impossible, right? And actually, if you look at the meaning of the energy at the time 0, there is no way you're going to have the sum of two positive numbers to be negative, right? So actually taking the energy negative in an oscillatory problem is completely stupid, because you cannot have it. How? What do you mean you're going to take it negative? You know, as someone who has no clue about the physics, you can say, oh, okay, so if energy is negative, okay, all right, I'm looking at the picture. I see that there is no way this graph is under the red line, so there is no motion. You see, I don't have to know any physics. Fine. Okay. So now, what about if h is 0? If h is 0, then, okay, let's look at an h0. So h0 is this horizontal line, h equals 0. Well, then in this case, the only possibility is for x to stay at 0, right? Then x, okay, of t will be 0 for all t, basically, because, you know, if you want to have 8x squared less equal than 0, this is only for x equals 0. There is no other possibility. Okay. And finally, if h is positive, right, so we have these three cases, okay, in this problem, then what? Okay, so let's take an h positive. So I'm taking an h positive. You see, there is no difference where I'm taking it, because they all kind of look the same. So here is an h positive fixed. Oh, then in this case, as I'm looking, x, right? So x has to be, right? We have 8x squared less equal than, let's say, 10, right? If I'm doing it, I'm taking h to be 10. Then I'll have here an x maximum if you want, and here a minus x maximum. So it's in the mirror, right? It's a, let's say, x min, okay? But this x min is nothing else but minus xm, right? Okay, all right. And then we can say, well, okay, so for this example, we would have x m, right, will be plus minus root of 10 over 8, right? So basically, we'll have that x is allowed to be in between this interval, right? So from little m to big M, right? So in other words, I'm allowed to move only in this region. So I already know, without solving the system, so x of t will be allowed to juggle in between, right, a minimum value and the maximum value that can be computed using the energy, right? So I can actually say that these guys are minus root of, I can actually say what they are, right? So in this example would be minus root of h over 8 and root of h over 8. So in other words, varying h, we can determine the possible regions of motion. They also called sometimes the Hills regions of motion. Okay. So, you know something, I'll stop here now because I think it's enough. I have another example. And next time I'll pick up with a more complicated example with the regions of motion. Okay. So not just this oscillator. And then, as I said, you know, next week there's just, you know, doing this chapter 1 and exercises, okay? So we have a lot to travel together about this stuff. So this being said, I'm done with this. Bye-bye.